Good afternoon. Welcome to the 6 day lecture of the Faculty Development Program on Manufacturing Technology Research and Management. So, on this date, we have two lectures. The first lecture will be delivered by Dr. Tanvi Saleh from International Islamic University, Malaysia. So, I would like to introduce Dr. Tanvi Saleh to the participants. Dr. Tanvi Saleh has been serving as an associate professor and coordinator of the Autonomous Systems and Robotics Research Unit in the Department of Mechatronics Engineering at the International Islamic University, Malaysia. Prior to joining IIUM, he worked as a postdoctoral fellow in the University of British Columbia, Canada. He did his Bachelor of Science in Mechanical Engineering from Bangladesh University of Engineering and Technology. Dr. Saleh did his master degree from National University of Singapore in 2005. He completed his PhD in 2009 from the National University of Singapore. During his postdoctoral research at UBC, Dr. Saleh worked mostly on micro-patterning of carbon nanotube forest, also known as vertically aligned carbon nanotubes (VACNTS). He is continuing his research on micro-patterning of VACNT for various applications in IIUM. His research interest also covers manufacturing automation and customized machine development, agile robotics for micromachining, machine learning for non-conventional and hybrid micromachining. His research is supported by various national and international funding agencies including Ministry of Higher Education Malaysia, Ministry of Science and Technology Malaysia, and US Air Force. He has supervised several postdoctorate students who largely contributed to his research. He is associated with several professional membership agencies like Board of Engineers Malaysia, IMAKE, IEEE, IEEE Robotic and Automation Society for Malaysia section. So I welcome Dr. Saleh for this FDP session. So I hand over the mic to Dr. Tanvi Saleh for delivering the expert lecture. So please, Dr. Saleh.
Thank you very much, Dr. Golam Kibriya, for your introduction and invitation for this lecture series. And I'm very grateful for that, for giving me this opportunity. And let me first share my screen. Okay, thank you very much, Dr. Kibriya, for the introduction. So today's topic that I'm going to discuss, the general topic is micro-electro-discharge machining. However, the specific topic that I have selected for today's discussion is more towards um, experimental research in micromachining through a case study on laser beam micromachining, LBMM, and micro-electro-discharge machining based micro drilling operation. So let us first give you a brief introduction about micro drilling and its application. So, micro drilling basically refers to manufacturing of intricate micro holes, which has a dimension in between 1 micrometer to 500 micrometer, according to Masujua. Um, Optical industry to create pinholes is one of the applications for micro drilling. So in laser applications or other optical applications, we need pinholes. So micro drilling is one of the options to be used. For also nozzles applications in automobile, aerospace, or 3D printers, they use micro drilling. And vertical interconnect access for various circuits, also we use micro drilling operation. Also for microfluidic applications, micro drilling is used. There are typical methods for micro drilling. One of the common methods is basically mechanical micro drilling, where manufacturer use mechanical micro drills to carry out the drilling operation. Um, Very recent, very popular technology is also laser micro drilling. Another one is micro electro-discharge machining. We have FIB, focused ion beam machining, also ultrasonic machining. So there are various technologies available for micro drilling operations, which can be broadly classified in um, tool-based and beam-based applications. For example, micro electro-discharge machining, mechanical micro drilling are mostly tool-based, whereas laser beam micro machining or focused ion beam machining are mostly um, beam-based micro drilling operation. Now, in laser drilling process that we have in our laboratory is basically a desktop fiber laser machine, as shown here. So we have a laser source. We have a vertical stage to adjust the focus of the laser source. This is the F theta lens from where the laser is being emitted. And we have a galvanometer, which basically two mirror to project the laser spot in XY direction. So this is how the laser spot being scanned through the surface and using this galvanometer. And once it is scanning, it can create a structure. So for our case, we try to create a circular structure like this. So the spot size of this particular laser is 40 micrometer in diameter, and the scanning speed between, the scanning spacing between each of the scan line is about 10 micrometer. And the program diameter that we programmed to make this scan was 200 micrometer. So this diameter was 200 micrometer. So this is the setup that we have in our laboratory. So it's a desktop, so it's not a very big machine. So the problems associated with this laser beam micromachining that we have found, because this is a nanosecond laser, it is not a very ultra short laser pulses, it's a nanosecond laser. So the nanosecond laser comes with the problems, as you can see here. The major problems are the recast layer. So it has a re-solidification of the molten metal that being ejected from this workpiece, and they create a recast layer. Also, this circularity is not very uniform. As you can see, it's not a very nice circle. Also, we have another concept of heat affected zone. So this is, as you can see, it kind of damages the surface, not only in the whole area, but the surroundings. So these are some of the problems that is associated with laser beam micromachining. So when you use laser beam micromachining to drill the holes, micro holes. And I forgot to mention the workpiece material that was used was stainless steel of 0.2 millimeter of thickness, and this program diameter of this hole was 200 micrometer. However, the actual diameter varies, depends on what is the laser power we use and what is the scanning speed we used. Now, so how to overcome this problem? Researchers also reported that the optimum processing condition, the ultra short laser like picosecond or femtosecond laser, can produce precise microhole with reasonable dimensional accuracy and almost zero or very reduced has heat affected zone and recast layer. But one of the major bottlenecks for ultra short pulse laser system is that very high initial cost, and further this type of laser is relatively inefficient when we want to drill very thick material, more than maybe 0.25 millimeter or so. So but costing is the main issue here. Very high initial cost for picosecond or femtosecond laser, and material removal is also very slow for ultra short laser system. So as I have mentioned in the previous slide, that the laser that we are using is a nanosecond laser. For this case, it's a nanosecond laser. So for nanosecond laser, we cannot achieve very high quality um, morphology of the drilled holes. Now, on the other hand, micro electro-discharge machining is another technology. Let me, in this slide, describe a little bit about micro electro-discharge machining. So in micro electro-discharge machining, we have a pair of conductive tool and a workpiece are connected via an RC pulse generator. So this is a tool which is conductive, electrically conductive, and this is the workpiece, and they are connected via an RC pulse generator. As you can see in this figure, the negative pole of the RC pulse generator is connected with this tool, whereas the positive pole is connected, as you can see here, the positive pole is connected with the workpiece. So the negative goes to the tool and the positive goes to the workpiece. This is basically the conventional EDM, where you want to erode materials from the workpiece mostly. So that's why we put negative on the tool side and the positive on the workpiece side. Now, the gap between the tool and the workpiece is filled with dielectric oil. As you can see, the gap between the tool and the workpiece is basically filled with dielectric oil. Now, when this tool approaches very close to the workpiece, there what happens is basically the dielectric barrier breaks down and the plasma forms, and that causes the sparks, and this sparks is repetitive in nature, and this spark basically erodes the material from the workpiece mostly uh, because of the electrothermal reactions. And the replication of the tool is basically carried out on the workpiece. So the tool is cylindrical, so a cylindrical hole will be created on the workpiece. And as we go along, there is a debris formed because of the electrothermal erosion of the workpiece, and that debris sometimes causes a short circuit. Instead of creating sparks, the tool basically touches the debris and it creates a short circuit, which is not healthy for the machining because it slows down the overall machining process, which we will see later on as well. So this is the basics of micro electro-discharge machining. Now, the comparison between LBMM, which is laser beam micromachining, and micro electro-discharge machining. So LBMM is basically a thermal ablation process. On the other hand, micro electro-discharge machining is an electrothermal process. LBMM is considered to be very fast as compared to micro-EDM is very slow process. On the other hand, the whole quality in terms of circularity, LBMM is poor, but micro-EDM is much better in terms of circularity for the case of as compared to the LBMM process. You have very high heat affected zone on the LBMM, whereas almost zero has, and there is no visible recast layer for the case of micro-EDM. LBMM, if is relatively costly. On the other hand, micro-EDM is relatively cheaper solution. So what we want to do in this research is basically we wanted to integrate these two processes so that we can kind of harness the advantages of both the processes. So we try to assimilate these two processes. So we want to do a sequential process. First, we want to carry out laser beam micromachining on pilot micromachining. So we make the pilot hole, and then finally we carried out the micro-EDM finishing operation to get the final holes. So this is the process integration. So we wanted to do this integration of the two processes. So we have both the machines. As I have mentioned, this LBMM setup is available in our lab. And also beside this LBMM setup, we have this micro electro-discharge machining system, which is equipped with an on-machine measurement device, OMM, with a camera, digital camera, and then optical lenses attached with the camera. So this is the schematic of the system. So we carried out the LBMM machining through, this is the workpiece. We carried out this LBMM machining, and then we transferred this workpiece into this Micro-EDM setup, and then we carry out this Micro-EDM finishing operation on this workpiece. So this is how we carried out the whole process, LBMM Micro-EDM sequential micromachining process. Now, one of the challenge of this process is that how should we relocate the tool of the micro-EDM so that it is right on top of the LBMM holes that we have created in another machine. So this is the challenge that we would like to overcome. And Alhamdulillah, we managed to come up with an kind of new idea with the help of this OMM system to relocate the tool right on the top of the LBMM holes. So as I have mentioned, as you can see here also, this is the OMM system, on machine measurement system. This is the tool. This is a spindle, and at the bottom we have the electrode or the tool for the micro-EDM operation. So this is basically the fixture that carries the LBMM holes. Then we transfer this fixture along with the workpiece in this system. So now I'm going to explain the whole the tool positioning system. So what we do here is we first create a random hole on this workpiece. So this is the first hole that we make, which we call for positioning purpose. So it's a reference hole. So once we make this hole, we know what is the position from the feedback from the from our controller. So we know exactly what the position of this tool here. Then what we do here is basically we bring this, then we shift this axis, because this is mounted on the x-axis. We shift this axis and we bring this camera right on the top of this hole, the reference hole. Because in the camera we have a crosshair, and so we can precisely locate the center position of this hole through the crosshair mark. And then we note down the position of this camera location, which is right on top of this hole. And then we shift this whole system in XY direction to any of the hole that which were previously machined by LBMM process. So these are all LBMM holes. So we bring this camera from the reference hole to any of the machine that we would like to carry out our finishing operation. So, and then we know the second position, and the difference between these two positions is basically the difference in X and Y direction from the reference hole. Now, as you know, the reference hole position of the tool here from this, as I have mentioned, that when we drill the hole, the reference hole, we know already the position. So we add these dx and dy with this reference hole coordinate. Then this tool becomes right on the top of the hole that we need to be finally machined with the help of electro-discharge machining process. So this is the way we achieve this tool repositioning process. And we found that it is quite accurate, and theoretically the accuracy is within the range of 2 micrometer because of the it depends basically on the accuracy of the stages, and the accuracy of the stage is basically 2 micrometer. So we can say that this repositioning accuracy is within the range of 2 micrometer. And this is a proof that it was the centering was quite okay. So what we did is basically we made a LBMM hole first, And then we did an EDMing operation on this LBMM hole. And we did not make the full through hole. And that means we did not complete the whole machining process. We stopped in the middle and took a picture to show that yes, it is right on the thing is the LBMM hole is actually on the center of this uh, hole, that is the EDM holes. So obviously, as I have mentioned, that EDM tool is larger than the LBMM hole. So our LBM laser drill hole was 200 micrometer program diameter, but micro-EDM tool that we use to fine finish this laser drill hole was 500 micrometer. So that's why you can see the 500 micrometer is bigger. This is bigger, and LBM hole is smaller. But the main thing to note here that it is in the center of this LBM micro-EDM hole. So the centering was correct. The way we have achieved the centering position, centering system, tool centering system. Sorry. Okay. Now, so this is a comparative result between the pure LBMM hole, pure laser drill hole, and this is pure micro-EDM, and this was the LBMM and micro-EDM hybrid or the sequential processing. So first, this is purely laser beam micromachining process. So as you can see, the quality between this hole and this hole are almost similar, with nice circular holes with less recurse layer or any visible hash zone. But here you can see a significant recurse layer, and also the circularity is not very smooth. So these are the problems associated with the laser beam micromachining. However, it can be achieved better if you do the fine finishing operation by micro-EDM. Now, then why do you have to go for micro-EDM, LBMM plus micro-EDM? Why not we just do the micro-EDM by itself? So that can be explained in the next slide. That you can see here that when we do LBMM micro-EDM, the time taken was significantly lower, which is 16.69 second, whereas when you do pure micro-EDM, it was almost like 3 times or more than 3 times higher, which is 60 minutes, 60.38 minutes. So in LBMM micro-EDM, it is only 16.69, whereas in pure micro-EDM, it was 60.38 minutes. So it's quite high. So that's why we can achieve a similar quality hole as same as the micro-EDM with the help of LBMM micro-EDM process. Also, we have seen that tool wear was significantly lowered down when we used uh, LBMM micro-EDM process, which was 5 micrometer, whereas pure micro-EDM, it was almost like 52 micrometer, the tool wear. So tool is expensive. So it is almost like 10 times the tool wear. So, and also another thing is that when you use LBMM micro-EDM process, the short circuit occurrence, we counted the number of short circuit, which was um, almost less than 100 times in the whole machining process, which is only 31 times it happened. But pure micro-EDM, it was like almost 1,000 over short circuit happened. More short circuits, it basically is not good for the machining process. It will increase the time of machining, and it gives other detrimental effect on the micro-EDM process. So these are the 3 things that we have monitored, and we have seen that LBMM micro-EDM basically shows better result as compared to pure micro-EDM. And obviously, in comparison with the quality, LBMM micro-EDM is much better quality as compared to the pure LBMM holes. Okay, now in our further study, what we try to do is we wanted to see how the LBMM parameters affect the performance of the secondary process. So now we have 2 processes. One is the primary process is the laser beam micromachining, and the secondary process is the micro-EDM machining. So in the laser beam micro machining, there are several process parameters such as laser power that you are using, the scanning speed of the galvanometer that you're using, also the pulse repetition rate. So there are several parameters that you can play with. And we want to see that how these parameters affect the secondary process performance, such as the machining time, such as the tool wear, such as the short circuit. So these are the things that we wanted to study. So what we did, so we wanted to do an initial parameter selection. So this was our initial parameter selection. So in the laser, what we did, we selected power in 60%, 70%, and 80%. This was, I think there is a typo here. It was not in watt, rather it was in percentage. So it was 60% and 70% and 80%. The actual wattage was 20 watt maximum, or yeah, 20 watts. So it was 60% of 20 watt, 70% and 80%. And then we did the scanning speed, we did in millimeter per second, which was 50, 100, and 150 millimeter per second. So, and pulse frequency or pulse repetition rate was fixed to be 10, 15, and 20 kilohertz. On the other hand, the micro-EDM parameters were all kept constant because we didn't want to vary the micro-EDM parameters. We just wanted to see how the laser parameters affects the micro-EDM performance. So that's why we kept the secondary process parameters constant. And the electrode diameter that we used for micro-EDM was 500 micrometer, and the electrode rotational speed was 500 RPM. The loop count is another parameter which we kept constant. So the loop count means how many times you can scan the workpiece with the laser spot. So we kept it constant and it was 75. And program diameter for our laser, as I have mentioned, was 200 micrometer. So these were the parameter we have selected. So I purposely kept these two things bold. So you can see the laser power was not varied very widely. It was from 60 to 80, and it was also 50 to 150 we varied. So they were not varied very wide range, rather in a narrow range we varied in our first initial parameter selection. And then we did find some variation as you change the laser power percentage and scanning speed. We did see that the entry area of the holes were varied. So if you use faster scanning speed, the entry area goes down, and if you increase the power, the entry area goes up, which is quite reasonable. I mean, quite straightforward to understand. Because what happened here is basically when you go faster scanning speed, the interaction time of the laser spot and the workpiece becomes less. That's why you have less penetration. But if you increase the power, of course, the penetration would be higher. So your entry area would be higher. So this is very straightforward to understand. And also, corresponding thing that we have achieved, we have seen is that at different scanning speed and different power, we saw that the variation of the EDM time. So we did see some range of variation. As you can see, at different scanning speed, you will see for different power, like for example, it's going down, it's also going down. So what it means is that EDM time was taken lesser and lesser. The reason is because when you use high power, so you have more initial penetration. When you go high power, you have higher penetration. And because of that, so initial material has been removed more, and you can have shorter machining time for micro-EDM operation. So this is the reason of that. But though we have seen some trend, but the variation was not very significant. It varied only from, you can see, 15 to 16 or little bit higher than 6. It's only 1 minute or so the variation. So this variation you can no not yeah, only a minute or so. The variation is not very significant. So this is the problem that we face, that when you try to report these type of results for a good journal publication, so there will be some question raised that what was your machining uncertainty, because this variation may come from the machining uncertainty also. So we have to measure the machining uncertainty, and we saw that this variation is within the machining uncertainty. That means you repeat the same machining process 3 times or 5 times, and you get the uncertainty by measuring the standard deviation. So we saw that the variation that we achieved is within the range of the uncertainty of the machining. So this is a lesson that we have learned, and that I want to convey to you as well, that we always have to look into this machining or measurement uncertainty when we get a result, basically when you want to do an experimental research. So so we saw that I mean, this is not convincing for us that we should report this result, because this is within the range of machining uncertainty. So that's why what we did in our next stage is basically, as I have mentioned, LBMM parameter does affect the secondary process. However, the percentage of variation is not substantial enough to overrule the experimental or machining uncertainty. Hence, we modified our experimental plan to ensure the substantial variation so that it can overcome the machining uncertainty. So in our secondary experiment, what we did is basically we, as you can see here, we varied the power in now 4 levels, and it is now varied quite wide range from 15% to 90%, which is actual power was varied around 6.4, 9.4, 12.5, and 15.5 wattage. And also the scanning speed was varied 50 to 1400 millimeter per second. As you can see in the previous, it was varied only 60 to 80% and 50 to 150. But then we varied here 15 to 90% and 50 to 1400%, 1400 millimeter per second. So this is the thing that we have modified our experimental plan. And pulse frequency we varied 5, 10, 15, and 20. And we did a full factorial experiment, and we kept our loop count constant. And EDM, we did not change anything. We kept the EDM process same as before. So then what we did is basically, then we try to see what happens here. So what we did is basically we saw that scanning speed and laser power does vary the EDM time. Basically, as you can see, now the EDM time varies with if you use higher power and lower scanning speed, basically you can get a faster EDM time. The reason is because for higher laser power and higher scanning speed, lower scanning speed will help you to do initial penetration larger, so more volume will be removed from the surface, and so you have to take less volume need to be removed during the EDM operation. We also notice another thing, interesting thing, that for various pulse repetition rate, there is no significant variation. So we saw that the pulse repetition rate does not basically create any effect on the system, on the EDM performance. So this is another thing. So next, all these cases, what we did, we averaged up all the pulse repetition rate. And then another interesting thing, once we averaged up the pulse repetition rate, then we tried to make a surface plot with the laser power and the scanning speed on these. And we wanted to see how these, we wanted to create a zonal effect that where would be the machining time zone. If you use a certain laser power or certain scanning speed to do the initial machining or initial machining of the laser holes. And then if you want to do the secondary process, so you can easily, from this map, you can easily detect, okay, let's say if you use a power of 15 watt and you use a scanning speed of 200, so your machining zone, your EDM operation would be in a range of uh, less than 20 minutes. So this blue area is basically less than 20 minutes, and you have here yellow, which is 55 minutes. But as you can see here, now the variation is quite substantial. It's varied in orders of magnitudes from 15 to 55 minutes. So it's quite significant, which easily overrules the any sort of machining uncertainty. And this map is important to select the parameter, because as you can see, you can go higher power and you can go very fast scanning speed. Still you'll be able to achieve the machining finishing operation within 20 minutes. So this is a significant, because you want to always try to lower your production time. So that's why from this map you can say, okay, I don't have to really go for, it is quite intuitive to know that if you do lower scanning speed and higher power, it will take lesser machining time by EDM. But from this study, what you can also say, that even if you use higher power and scanning speed, you don't really care if you can go as high as possible, which is for this case 1400 millimeter per second, still you'll be able to achieve the finishing operation within 20 minutes. So, and in that case, obviously, any manufacturer will try to go as high scanning speed by laser as possible, so that the overall production time is lessened. So this is the we have done this, and also we have also shown the machinability, just to give better understanding, that we measured the machining pulse frequency. That means that during the EDM operation we use an high frequency ammeter, and that ammeter help us to measure the discharge pulses, help us to count the discharge pulses. And we saw that that the discharge pulse also increases here when you use higher power and lower scanning speed. So because of the higher discharge pulses, basically you have better machinability by EDM operation. And why these reasons, why we get this value that we were seeing? The reason is pretty straightforward, because when we saw that as you increase the power, you can see the entry area of the laser machine hole increases. However, the entry area is not the main factor. With different scanning speed, it doesn't really change much. But in the case of exit area, that means the laser hole has an entry area and the exit area. Exit area has significant variation. You can see when we go faster scanning speed, actually the laser cannot penetrate at lower power at all. So you can see these things almost like zero penetration. So that's why you have to the machining time was higher for EDM operation when we use basically low power and faster scanning speed. So the machining time was higher because there was not much of penetration at all by the laser process. So, and we can see this proof from here as well. So here you have a full penetration, but here not full. Partial penetration here is almost like no penetration, no full penetration at all in these two cases. So that's why we can say that when you don't have much of penetration, then EDM finishing operation takes longer time, much longer time. And so the overall volume also we measured instead of pure entry and exit area, and we have seen that overall volume is also increased with higher laser power and lower scanning speed, and hence the EDM operation was shortened when you use higher laser power and lower scanning speed. And then we also measured the tool wear, and we saw that tool wear and short circuit reduces quite significantly when you use higher laser power, because you can use higher laser power, and then when you do the EDM operation on these holes, pre-machined holes, you can see the short circuit and tool wear goes down significantly as from these graphs. So the reason being is basically because the tool wear and the short circuit, we have measured a correlation. They are highly correlated with the EDM time. So the longer the EDM process, the short circuit and tool wear was higher. The correlation was 90 over percentage. So that we can say that it's very highly correlated. So because when you use low power and faster scanning speed, you need to do a longer machining time by EDM. So when you have longer machining time by EDM, you basically enhances in a negative way the tool wear and the short circuit. So that's why basically it happened. Also, interestingly, we saw that not only the gross tool wear or the short circuit, the rate also changes. The rate of tool wear also changes. So when the laser power and scanning speed were used, higher laser power was used for pre-machining, and lower scanning speed, the rate of tool wear was basically the tool wear was reduced. Rate of tool wear was measured by micrometer per minute, and also short circuit was reduced. As you can see, the number of short circuit per minute occurrence was also reduced. So this is also another finding that we highlighted, that not only the gross tool wear or the gross short circuit, but also the rate of the tool wear and the short circuit. And okay, so I think that's all that I wanted to share with you. So in conclusion, what we can say, Alhamdulillah, we have shown a methodology to reposition the workpiece accurately after carrying out the LBMM process. So this methodology can be used to be implemented for any type of sequential process with the help of OMM system. And we also defined an experimental zone that for the LBMM process parameter, which can be used for faster finishing process by Micro-EDM with lower tool wear rate and short circuit rate. Another lesson that we have learned, that in experimental parametric study, we should think about experimental uncertainty before we publish our result. So we always have to look into the experimental uncertainty, whether our results can really overcome the experimental uncertainty or not. Um, that is all from my side. I think thank you very much. And now I'm open for any Q&A. Thank you.